Hey, hi, welcome to the third part of the wind energy. Right, so we were discussing about lift to drag ratio and what's the concept behind coefficient of lift and coefficient of drag and how is it responsible to maintain the efficiency of the wind turbine. Now carefully see the angle that the relative wind is making with the chord of the wind turbine blade element. Now this angle right over here, this angle is nothing but angle of attack. So let's write it down. That angle is called as angle of attack and we represent it by alpha. So just imagine this alpha is purely dependent on the angle of inclination, which we call as phi. This is the angle of inclination. Now this angle of inclination is the function of the wind velocity and the function sorry and the function of the linear velocity at which the element is traveling. So you have to understand that wind velocity is random in nature. R omega, which is the linear velocity of the element, could be anything, right? So phi itself is random in nature. It keeps on changing. It keeps on changing according to the velocity of the wind. So what we are really interested is we want this alpha to be the best. Now what is the meaning of the best? The best means we want it to have the best possible lift to drag ratio. So here we have the data of a wind profile of NACA 0012. Now this data is of NACA 0012 at a Reynolds number of 80,000. Now always bear in mind, when we design a wind turbine we want a Reynolds number which is around 40 to 80,000 because we don't want Reynolds number to be very high because this is a wind turbine. So you can imagine that the velocity of the wind compared to the velocity of wind which is experienced by a wind turbine is very less as compared to the velocity of the wind which has been experienced by, say, an airplane or a jet. So that is the reason Reynolds number has to be low, isn't it? Because it's rho VL upon mu. So V is extremely less. So yeah, the Reynolds number should be around 80,000 or say 40,000. So right, this is the data of NACA 0012, right? 0012 at Reynolds number of 80. Now if you have a look carefully, you would realize that there is something called as coefficient of lift and there is something as coefficient of drag. What is the meaning of coefficient of lift and coefficient of drag? What does it mean? Now what it really means is purely when just imagine that there is a relative wind. That means this is the actual wind which is being faced by the blade element. Now when it faces this wind, what really happens is it experiences a lift. Now that lift is perpendicular to the direction of the wind. Now this is our interest. This is what we are really interested in, because this lift force, this is the coefficient of lift, which then multiplies by the other factors which gives the lift force. We'll come to it later, but for now just think that this is the lift force which is responsible to generate the power. Now this lift force is perpendicular to the direction of the wind, relative wind, which is being experienced by the wind turbine. And there is another force which is parallel to that of the direction of the wind, so it is in this direction. So this is nothing but the direction of drag force and also the direction of the wind. On the other hand, this this is the direction of lift force. This is the direction of lift force, which is extremely important, which is going to generate power. We want lift force to be as good as possible. We want lift force to be good. That means we want that the ratio of lift to drag coefficient or lift to drag force should be maximum. So what really happens is, if you carefully observe this table, you would realize that at different angle of attack we have different lift coefficient and drag coefficient. So what we are really interested is to have the best lift coefficient, so we have to see the best lift to drag ratio. If we carefully observe, we observe that at 7 degrees, this is where we want to be. This is exactly the angle we are looking out for. We want alpha to be 7 degree no matter what, because whenever the alpha is 7 degree, it will give the best possible lift. So now we can feel that how important this angle alpha is, and we want this alpha to be the best. In this in this blade profile at this Reynolds number, we know that the best possible angle of attack that we can obtain is 7 degrees. So this is our target. This is where we want to be. This is the angle we want to achieve no matter what. So the question is, now I'll show you. Let's see the graphs of coefficient of lift and coefficient of drag, so it will give a better idea. So let's observe the graph. So this is the graph. This graph right here, as you can see that this blue line is the lift coefficient and this red line is the drag coefficient. So as you can see that around 7, 6, 7, 8 degrees the lift coefficient is maximum, and then suddenly the drag coefficient takes off. But what we are interested is the best possible lift to drag ratio, and that is this graph right here. So if you observe this graph carefully, you will observe that at 7 degrees we have the best possible lift to drag ratio. Now see what happens. After 2-3 degrees it suddenly goes down exponentially, isn't it? So we don't want that to happen. We want that our angle of attack should be somewhere here, should be somewhere around 7 degrees. So the question is, how do we manage to achieve it? Now that is the question. Now it will become very interesting when we try to maintain this angle of attack. So I just wanted to let you know how important this angle of attack is in this video. So now we can say that this angle of attack should be 7 degrees. This is what we want. This is our intention. So how is it possible for us to manage this objective? Now I'll just give a brief idea. Now just imagine if, now we know that this guy right here, which is angle of inclination, is the function of wind velocity and tip speed, which is r omega. Now both these guys are random. We can't control them. They are random in nature. So you can imagine now that phi is also random. Phi keeps on changing with as the wind speed changes. So as phi keeps on changing, naturally the angle of attack will change, isn't it? Angle of attack has to change as this angle of inclination changes. So what we do is, somehow we want to control this angle. That means if somehow we can control this angle with respect to the change in wind speed, that means with respect to the change in phi, which is angle of inclination, we can maintain our objective, which is to have the angle of attack 7 degrees. So that will cover in the next video. It will become very interesting to observe how it is possible to maintain this angle 7 degrees. If somehow we can do it, we can assure that we will achieve the best possible coefficient of power. So in the next video we will discuss the pitch angle and the twist angle. So for now, let's see, alright, so let's finish this video right now, and